We're now going to do a new type of problem called the root finding problem. It's another very common problem type that one encounters. Let's start with an example. So as an example, we'll use a type of financial investment called an annuity. So in an annuity, you have a predefined contribution and a predefined payout. So if you deposit P dollars every month for N months, and the interest rate, the annual interest rate is quoted to you as the number I, then the return that you get at the end is called capital M, and it's given by this formula here. Okay, so let's take a scenario where we do it for 20 years, so N is 240 months, and you want to pay in $150 each month, and at the end you want an investment that's worth, say, $200,000. What would the interest rate have to be in order for you to get that? So we could solve this problem, or we could pose this problem, I should say, as a root finding problem, which means to find the root of a function. So we define a function of the interest rate, little f of I, okay, and we're just taking the difference between M and the its expression in the formula for the annuity, right? So if f is equal to 0, the annuity equation is satisfied. That's why we define the function as the way that we do. Okay, so now the goal of our problem here is to find the value capital I, which is a root of f, in other words, that makes f equal to 0. And you can see, if you look at the formula for f of I, it's not something that you would be able to do algebraically because of the I in the denominator out in front and the I to a power, 240th power. You won't be able to find the inverse function by a formula, which is usually the case. So you could think of it as finding a single value of the inverse function, right? I is the value of the inverse function at 0, but we do it by not by trying to find a formula for f inverse, but by doing it through other methods. Root finding problems come up in this kind of thing where you have a particular goal to satisfy that you're trying to achieve, or there's some constraint on your system that has to be satisfied. That's a nonlinear function. Okay, so anytime we get a new type of problem, it's worth asking how's the conditioning of that problem? What can we expect in the presence of round-off errors? In this case, we have to talk about the data to the problem as being the actual function f of x. So we have a function f of x, and the solution that we're looking for is a root of that function. So let's call that value r for root. So r satisfies the equation f of r equals 0. So the data to the problem is a function, and the output of the function and the result of the problem is a number. All right. So our informal definition of condition number is some norm of the change in the result divided by the norm of the change in the data that created that result. So that's our informal definition. Then we have to turn it into something more mathematical. So first of all, what does it mean to perturb the data? Well, the data is a function, so that we could think of perturbing it as adding another function g of x. So I should say that this is all now being thought of in terms of absolute condition number. We might well want to consider relative condition numbers when we do floating point arithmetic. It's just that the math is a little easier in the absolute case. So that's where we'll be. Okay, so if we change the function f of x to f of x plus g of x, that might change the root. And so the root will change into r plus delta r. So what we do is we say that now the modified result, or the changed result, r plus delta r, has to satisfy this new equation, where it's a root of the perturbed function. Okay, to make some progress with this, we're going to linearize the function f, so that means we're just going to replace f of r plus delta r by these two terms. This is the linearization of that function. Should be valid for small values of delta r. it's an approximation, but we're just going to keep writing it like it's an equation. Okay, and then we just rearrange using the fact that r is a root of the original function f. And so that first term goes to 0, and we can solve for delta r. So delta r really is the change in the result due to the change of the problem, or change of the data, f going to f plus g. Now, to get kappa, we have to take some kind of norm in the change of the result. Well, that's just an absolute value. That's easy. What about the change in the data? How do we measure that? Well, without getting into the technical details of it, it seems pretty reasonable to let the value of g represent the change in the data. Certainly they seem to be related, and if we just take it as equality for the relationship, then at least we get some sort of reasonable estimate on kappa, or some usable form for kappa. It's just 1 over the absolute value of f prime and r. So that means that the solution is to the root finding problem, the root itself will be highly sensitive to the function that's input whenever f prime of r, the exact function, is close to 0. So there's a pretty simple graphical explanation. Of why this matters. So let's take a case where we have a function with f prime fairly large at a root. So there's our root r. And here we have f prime of r is quite large. So we'll write that as much bigger than 1, let's say. Okay, if we perturb the function, okay, that means at each value of f we might go up or down by a small amount. So we have this tube around the original function. Right? And in this tube, we're saying that the function f plus g wiggles around somewhere inside of here. Okay, what I drew there actually violates the vertical line test, so that couldn't possibly be it, but you get the idea. Regardless of what it actually does, the details of what it actually does when it's perturbed, we can say that the root lies somewhere in this interval. So the root of the perturbed problem, f plus g, lies in this interval. And if you compare that to the width of the height of the tube itself, okay, it's actually no bigger, and maybe it's smaller in the way I've drawn it here. Okay, so it should be, no larger than the thickness of the tube. On the other hand now, the opposite situation, where f prime is fairly close to 0, here, okay, so now we have f prime is much closer to 0 at the root. Okay, now if we draw our tube around the function, whoops, that's supposed to be green. Okay, so our actual function wiggles around in there somehow. And I haven't drawn it perfectly, but you'll see it doesn't really matter that much. So now what we can say is that the root of the perturbed function lies anywhere in this interval. And you can just kind of see from the geometry of the thing, right? In fact, f prime is the thing that relates the width of that interval to the thickness of the tube here. Now it's much thicker. So in other words, there's much greater uncertainty in this case. In the root than in the original function. That's what we mean by the condition number, right? We could think of it as perturbation, or we could think of it as uncertainty, measurement error, whatever you like. Whatever the cause, changes in the function are amplified when it comes to the root. Also, let's think about the extreme case of f prime equaling 0. Okay, whoops, that was a little... f prime of r equals 0. Well, in that case we say r is a double root, or at least a double root. So a couple different ways we might think about that. So for example, if you think about a polynomial, that would mean you have a quadratic term rather than just a linear term for that root. Or if you think about it in terms of the Taylor series of f at r, and we're going to be seeing this quite a bit, so you may have to think about our little review of power series and Taylor series. So this is the formula for f at f of, yeah, that's right, I did one right, f of x. So it's equal to f of r plus f prime of r times x minus a plus 1 over 2 factorial f double prime of r times x minus a squared plus 1 over 3 factorial f triple prime times x minus a cubed, etc. Well, if f is a root, if r is a root, that first term is 0. If also f prime of r is a root, r is a double root. And the first term is not the linear term. The first meaningful term in the series is this quadratic term. Okay, so it's a fairly special, unusual circumstance. But we can say that if that occurs, if the function actually has, for example, a critical point, a minimum value at the root, right? If at the root we actually have a minimum value, so the derivative is 0 at the root, well, now you see that a disaster could occur. Any perturbation that lifts that curve upward, no matter how small, makes the root disappear completely. So any size perturbation might make r vanish. And so this would be the ultimate in what we call an ill-posed problem. It's something that you can't expect necessarily to answer accurately using a computer with floating point arithmetic, because any kind of perturbation whatsoever can completely change the character of the solution.